Hey, we're talking now about the construction, how we can get long message max from short message max. This is construction 4.9 from the lecture. And the idea was that we first constructed this mac for short messages, namely messages of length n. And we did this with just a PRF. So a tag for message m is just its PRF value. And as a second step, we want to take this mac for messages of length n and come up with a mac for messages of essentially arbitrary lengths. And this is all knowing that this construction probably won't be used in practice anytime soon, because usually we'll have like collision resistant hashing, and then which we will see later, and then all of this construction will just be kind of deprecated. So this works, this nice theoretical construction. It shows that we can actually, using only PRFs, construct max for arbitrary length messages, though in practice it isn't all that important. And this is the construction right here. And the question will be, what is actually the role of all of these components that we use in this mac? So what's the R for, what's the L for, what's the I for, what's the MI for? And the questions that I will ask you will be, what happens if we omit, for example, if we omit R from this? So the mac would just be a mac of L, I, and MI. What happens if we omit the L? What happens if we omit the I? And what if we omit the MI? And then for each of these omissions, you can come up with an easy adversary that will basically break this construction. So let's start with what happens if we omit the L from this construction. So imagine this. There's essentially, we don't add the L into this mac here. And now my question is, can you attack the resulting mac? Okay, this attack is actually not too difficult. The idea is that if we don't authenticate the length of the message that we wanted to make, basically this whole thing will become prone to truncation attacks. So I can query for a mac on a long message and essentially just make this a mac on a shorter message. So the attack goes like this. So the attack is pretty simple. We query for a long message, in this case consisting of two messages, M1 and M2. We will get this tag according to the mac definition here. But in those tags ti, there's no L, let's say. And then the idea is I can just throw away the T2 and then just sell this whole thing as a mac on only M1. And clearly M1 is not the same as M1 concatenated M2. So in the mac security game, we would win. Now for the next part, let's say we omit the I. So in the mac, we won't add the index I for the message that is made for ti. What happens then? How could we then break this whole scheme? So the I is in there to make sure that an adversary cannot mess with the order of the tags or the order of the messages. So an attack would just go like this. So I can just query the oracle for like M1 concatenated M2. And then I can basically just switch the T1 and T2 around to get a valid mac on M2 concatenated M1. So this is the role of the I in this whole construction. So it makes sure that we can't change the order of the blocks that we're making. So we could also take a look at what happens if we omit the MI in the mac, but I'm pretty sure you can figure that out, that it's not a good idea to have a mac that is just independent of the concrete messages. So I'll skip this and we'll directly jump to what happens if we omit the R. So normally in all of these macs, whenever we make a new long message, we would choose a random R and then include this R into every mac of every block. So why do we do this? How can you break this whole thing, assuming that we wouldn't make the R? So do you have an idea? It's actually slightly more complicated than the other ones. So essentially this R makes sure that if you query for tags on 2 long messages, that you can't take like some of the block tags from the first message and insert them into the MAC for the second message. There, the idea is that for the first query you will have one R authenticated, and in the second query you will have a different R, so very likely a different R authenticated. So it should be impossible to insert one of the blocks from the one message into one of the blocks for the other message. And we can actually attack this using exactly this idea. So let's say all of the M1, M2, M1 prime, M2 prime, they're all distinct. So now there's no equalities between them. And then the attack is just I query for M1 and M2. I query for M1, M2, and then for M1 prime, M2 prime. And then I do the mix and match thing. So I just take the T1 for M1 and the T2 prime for M2 prime, and I just combine them to get a tag on M1, M2 prime. And yeah, if I do add the R into this MAC, then this attack won't be possible because the two R's. So these two MACs here will have a different R, so the verification would just like reject this. Okay, so this is why each of these components is in there, and why we can't just like leave out the R or the L or the I. They each play a very important role in making this whole construction secure. Thank you for your attention, and see you next time.